Hello and welcome to an FPGA vision lecture. In this video I will show you how an algorithm can detect the lanes of a street. And if you have a look in the literature, you will see that the main algorithm that is proposed for this task is the Sobel filter. So we will implement the Sobel filter as an algorithm in C to check how it is suitable for our application of lane detection and what parameters we need for an FPGA implementation. The basic operation of the Sobel filter is depicted in this graphic. You have a matrix for horizontal and for vertical processing, and both are working on a 3x3 image region. These are then combined by taking the square of both parts and taking the square root. And then you get a value g, which corresponds to the strength of an edge in the image. The next step would then be to combine the different edges you have in an image to find lanes. And this is usually done by the Huff transformation. The Huff transformation is a transformation between your image region, where you have the different edges, into a Huff space where the edges you are having are sorted or are represented due to their position and their angle. We will not cover the Huff transformation in this FPGA vision lecture. We will focus on the lane detection, but of course, if you're interested, you're welcome to expand the algorithm to really interpreting the edges and also finding then lanes in the image. For evaluating the algorithm, we need some test images. And for this video, we have a look at 3 different images. The first image that you see here is a motorway in Germany, 2-lane motorway, and visibility is good, so the algorithm should work quite well. The second image is a street in Spain, and again visibility is good. You should again be able to extract the lanes quite well from this image. And the third image we use as a test image here is a lane in Denmark. Here visibility is not so good, so the algorithm might have some problems, but this is also interesting to see how stable the algorithm is and how it handles situations that are not ideal. Let's have a look at the first test images and apply the Sobel algorithm to it. We have a look in the detail of one of the images, and here we see part of the street where we want to find an edge. We see that the road itself has RGB values of about 150, and the lane markings, which will show us where we have the boundaries, have RGB values of 220 for RGB. And you can translate that from RGB domain into the luminance by having certain factors, as you see in this image, for RGB. And as RGB in this simple application all have the same values, also luminance is 150 and 220. So let's consider a vertical edge. We have some pixels with a value of 150, others with 220. And if we take the Sobel filter, we get from the horizontal filter a value of -280, and from the vertical filter we get a value of 0. So if we take both values to the square, add them, take the square root, we get a value of g with 280, which is an indication of the edge we have here. We can do the same processing for other configurations. So we have in this image some edges that are not vertical but that are diagonal or on a slope. You can do some calculations what values would be resulting from such a configuration. Take a paper and a pen and calculate it yourself. No answers are given, so just check it for yourself if you're interested. And this gives us an indication how the algorithm will perform. This is just for our understanding of this algorithm. So the next step would be an implementation as a C program. We take our test images and we let this algorithm run for a number of test images. And this is exactly what I have prepared for you. So you have a C file which does the following processing. First you open the test images, then you have a loop for all pixels in X and Y for the image, and for every pixel you do a processing of reading the pixel around the current position. You convert the RGB to the luminance, you perform the Sobel filter, write the resulting value to the image, and then after you completed the loop, you write the complete image back to the file and can check what the result of your processing is. To visualize the results, we want to have an image of the edges in the street scenes that we're seeing, and as we saw, a typical value would be something like 280. We want edges to be visible as black, and when we have no edges, we want to have a white pixel at this position, because this gives a nice image to check the algorithm. And therefore, we calculate an output pixel, we divide G by a factor of 2, and then subtract this value from the white pixel, which would have a value of 255. All this has been programmed for opening and handling the test images. We use a package called BMP24_IO, which is available on SourceForge. All calculations have been done in floating point, because that's at the moment easier for us to do. You can find the C file under the name of lane float, and it has been verified with the GNU-C compiler on Cygwin under Windows 10. So let's have a look at this processing. Here is the program code. We don't go into details on that. You can have a look at it on your own. So here you have a terminal where you can compile the C file. GCC lanefloat.c. Then you can execute it and give the name of the test images as an argument. And you can do this for different images to check the performance. So now we have a look at the results of this filtering. Here you see the 3 different test images again. First, the motorway in Germany, and this is the result of the Sobel filtering. You see that the edges are clearly visible, so apparently the algorithm is working. This is the road in Spain. Again, the algorithm is working fine. And this is the scene which is a bit critical, the bridge in Denmark on a rainy day. So still you see some edges and the result is quite okay. You might have to adjust the values for detecting a lane. So this would be a task for the system later on that interprets the result of the Sobel filter. So now you've seen how an algorithm works that detects lane boundaries in a street scene. And I invite you to have a look at the other videos in this lecture, where you can learn how to implement such an algorithm on an FPGA and verify it. And you will also have the opportunity to try out the algorithm on a remote lab. So yeah, have a look at the other lectures, and I hope you find them useful.